Okay, let's get started. So last class we ended, we were trying to dig around that nice 500-page EPI exam, the handbook, right, that they hand out. Because we were trying to look for steady state error table. And on page 231, hopefully you all can see that. Does that table look familiar? It's the ESS table, right? It even says it at the top. Steady state. Well, I guess I can't highlight it here. It says a steady state error, and then it breaks it down based on the input, right? So if it's a step, ramp, or parabolic, as well as the system type. Remember, the system type is the number of integrators. So it gives you this table. What perhaps is missing in here? Go up a little bit. Anybody see what's missing? I'll go back down, but I just want to see. Start here at the beginning of control systems. Hey, B. Good morning. Good. So we have a table. What's missing from the table? The table's complete. Anybody know what case of B is? Does anybody see case of B? So the problem with this table, you don't even know what case of B is, do you? So this has an incomplete, in my opinion, information. It might be defined over here as well. Like it might be defined in that term, but it actually doesn't tell you what case of B is. And there's another problem with this table. Are these all correct? Are those all case of B's? No, over here, that should be our position constant. This should be our acceleration constant, our velocity constant, sorry. And that should be our acceleration constant. So I didn't go too far up to see where that actually goes in terms of the definition of case of B. But maybe you can define it from here because it says case of B over S. I mean, it does say an open loop transfer function, which would be the G term. And it has some poles and zeros here, which is fine. And then this T, I'm assuming would mean the system type, right? You can see that's over here. So, but the problem with that is, how does that tell you what the value of case of B is, right? I don't see that over here. So maybe if this was the case of B term, that would help a little bit. But again, the problem is we still have to multiply that case of B term by S or S squared to get the other term. So I think there's a mistake in this section. I mean, I'd have to really dig through and see if it's there. But at least in terms of the control systems, unless they define case of B someplace else, I think this section's got some errors in it. And it's not complete. So maybe that's why they want to make it more challenging for you, because usually doing the ESS stuff is fairly straightforward once you use this table. But if you don't have a complete picture of the table and maybe have some incorrect information, it might make it more challenging. But anyway, if you do take the FE review manual, just remember your case of B term, right? So my case of B is equal to the limit as S approaches 0. Our open loop gain, which in this class we call it GP times GC, because you might add a controller to your block diagram. And then KV is equal to S times KB, and I'm just using the B term because that's what's shown in the table. And then KA is equal to S squared times KB. All right. So if you're just trying to use that table, you know, it's kind of a modification. But that's on page 231 of this manual, the manual that I have here. Oops, let's go to page 1. I don't know if this is the latest and greatest, but this is version 10.0.1. At least so if you're looking for where that table is, you can find it in the instrumentation section. under, and it's on page 231 specifically for 10.0.1. All right. So that kind of finishes up the last. Any last minute questions before we have our exam tomorrow? Hopefully you spent the weekend studying. You're all prepped and ready to rock. Yes, sir.
Possibly look the setup to a percolates with a variable K.
Yeah, well, there was one of the homework problems, right?
Yeah, that was this one. Kind of go over it.
Yeah, let's bring up the homework one. That was a pretty, hopefully a pretty good one. And let's see. Which homework was that?
Yeah, so
Okay. So look at problem number 3. Here's our characteristic equation right over here in the middle. Let me go ahead and annotate. So here's our characteristic equation. So we know that we have an S4 row as our highest S term. So, well, actually, the first thing we do is it says find values at K that result in a stable system. So the very first thing I need to do is I know K needs to be greater than 0. Why? Say that again, Noah. I think you said it, but yeah, you can't have any sign changes in the characteristic equation. That's the first necessary but insufficient condition, right? The other thing is it's got to be greater than 0. Why does it have to be greater than 0? No term can vanish, right? So really, it's not the fact that it has to be that, if K is equal to 0, that technically is not a sign change, right? Because 0 is not positive, nor is it negative. So it's not officially a sign change. But if K goes to 0, then we have a term, a coefficient that vanishes, right? So it would be not a valid number. So no, it's going to be greater than 0 to start. Now, we look and we see that there are no sign changes in there. So there is the possibility that K can be a value that will result in a stable system. All right. So you kind of just your high level first inspection, don't just jump in and build your Ruth Hurwitz approach. Actually go in and see, does this, can I look at just the characteristic equation and make some assumptions about, can I even do this? And then you just write it down, right? If this was a negative 11 over here, no, Paul, there's no values of K. That's a valid answer. There's no values of K that result in a stable system because you have a sign change in the characteristic equation and because of one of the necessary but insufficient conditions that states you only have to have all positive or all negative coefficients. There's no value of K. So I don't even have to do the work, right? You just proved you understand the concepts without even have to doing the work. Everybody understand that? Mason and Branson, go ahead. I would double check the study guide, but I'm pretty sure there will be. Go ahead.
Kind of what you just explained, how you said like you don't really have to do out the problem to
If you have enough intelligence.
if you have enough information based like just viewing it, you can make an assumption.
It's not an assumption, is it?
It's kind of you're proving that the system is unstable by looking at size and zeros of the characteristics.
I would just say there are the two necessary but insufficient conditions. If either one of those is not met, I can't make this a stable system. If the question was, so here's the question, what if there is a negative 11 in here? And what if the question was, how many poles in the right-hand half plane? Then you can't use those because the question is, I don't want to know if it's stable or not. I want to know how many poles are in the right-hand half plane. Then you'd have to do the Ruth Hurwitz approach. Everybody understand the difference? One is, can the system be stable? The other one is how many poles are making it unstable. Okay. All right, so grab my coefficients, the ones from here. The 6 goes in row S3 because we alternate, right? Or we skip. Then we have 11, 6, and then K. All right. So now we go and start building my determinant. And I get a little bit fancy over here, but technically to solve, I'll call this A. It's -1 over the element right above, 6, times the determinant, 1, 6, 11, and 6, correct? So when you do that, you have -1 over 6. This becomes 6 minus 11, right? When you do the determinant approach. And then this becomes 11 minus 6 over 6. All right. Whoops, wait a minute. 6 times 11. So 6 times 11, sorry. And then when you do that out, you should see that that's equal to 10. Over here, I kind of simplified it a little bit. I moved the negative sign in here right from the beginning. That's why it's 6 times 11 minus 1 times 6, right? So the math is correct. I just kind of skipped the step of showing the determinant and the negative number, and you go from there. So there's 10. Then I do the same thing over here, and hopefully you see that you can get the value of K by multiplying it out. Then I move to the next row. So it's the -1 over the number that's previous to it, and then the determinant of the 2 elements that are directly above and the 1 to the right. So 10 times 6 minus 6 times K divided by 10. And then I don't have any more coefficients over here, so it's just going to be 0. And then my last one gets a little bit messy, but I'm kind of being meticulous about it. So you can see with all this gibberish, I end up with K. Sanity check your work. Remember what the rule is for Ruth Hurwitz. Your last term in your characteristic equation should be your last row term. There was a student that stopped by the other day that had a negative K in there. I believe it was negative K. And, that was one of the things, which is you probably have some sort of algebra error because it's not a negative K, it's a positive K. You can check it from there. All right, so we've already determined that this one here means that my K had better be greater than, or I said greater than or equal to 0, but we know it has to be greater than. And then the next thing we need to do is go up over here, right? And that row, 60 minus 6K over 10 has to be greater than or equal to 0, right? So do everybody want to see the algebra on this, or they feel like they can do it themselves to solve for K? I need an answer. Want to see it? All right, so what happens to the 10 in the denominator? When I multiply both sides by 10, 10 times 0 is 0. So I can even forget the denominator, right? And again, this is just a suggestion, but whenever you multiply by an equality by a negative number, you have to swap the equality around. So what I like to do is drag over any numbers that I can, so I don't have to multiply by negative numbers. And so K has to be less than or equal to 10. Everybody see that? That's super duper important. If I move the 60 to the other side, so I had negative 6K, yeah, if I would have done this way, so that would be negative 6K has to be greater than or equal to negative 60, right? The thing you would say is K is greater than or equal to 10. How can these things be the same? Well, the thing about algebra, when you multiply equalities with negative numbers or inequalities, it swaps that around. You remember that in algebra? I would be shocked if you did. Because half the time you don't even teach it. And so what I tell people to do, instead of trying to multiply, and it doesn't matter if you multiply, by any negative number, you have to swap the equality around. So what I try to do is I just try to move, if I can, I try to move things onto the other side of the equalities to get rid of those negative numbers. And I don't do that to be difficult. I just do it because it's like, well, most people will forget you need to multiply by, the equality has to change direction. So you don't multiply by any negative numbers, and you're good to go. And so that is here between 0 and 10. K has to be between 0 and 10. Then I said for it to be a marginally stable system, you have to have a row of zeros over here, right? What makes that a row of zeros is when K is equal to 10, correct? Because when I set it equal to 10 over here, in this evaluation over here, 60 minus 60 is going to be equal to 0. So if I have 10 over here, I go 1 row up. So I have 60 minus, other row above that. That doesn't want to erase. So where's my erase button? So I'm going to go and I've got a row of zeros here. So I grab the coefficients from the S2 row, 10 S squared plus 10 equals 0, right? That's the auxiliary equation. This is A of S. So now I set that equal to 0, and I can see S squared is equal to -1. S is equal to plus or minus J. And those are the complex, those are the poles when it's at its J omega on the J omega axis, which is right here. Okay, does that answer your question? Any other questions? Yes, sir.
On the previous problem, for solving for S1, are you just throwing out the 2 times 10 and so marginal number, like basically 0?
Yeah, when I compare a really little number times 10, which is still a really little number, and I compare that to 200, I throw that in the trash. I can't throw that in the trash over here, right?
No, I got that. I just didn't know.
Yeah, you can keep it. Yeah, you can certainly keep it, but whenever you're comparing it to normal quote unquote numbers and you're adding or subtracting, you can delete it. When you multiply, it's harder to, or divide, it's hard to delete it. Okay. Any other questions? Yes, sir.
Get a 0 to the left column. It's not.
The left column, you mean the first column?
Yeah,
Okay.
You're not always supposed to use E, right?
No, you only use E when there's a 0 in the first column, right here. Is there a 0 in the second column? No. So I use the E term over here because the first thing I did was check to see if in the second column there's also a 0. Since it's not, it's a 20. Then I got to go ahead and substitute an E. So what I did is I did this process right here first. Then I did this and calculated that that's not a 0. So then I did this last little bit here. I made it equal to. You use the auxiliary equation. That's this part right here. See, there's both zeros here. So that's when I have to use that auxiliary equation. Okay. Anything else?
If it was E, and we get a number for the second column, we would have solved that number with 0, not E, correct?
No.
No, we could use E. Still get a number?
No, if the first column is E and the second column is not, I mean, the first column is 0 and the second column is not, you use E. If you're both zeros, you can't use E. That's what I'm saying. You can't use the E term.
Okay, but if the second column is not E.
The second column should never be E.
Sorry, I mean, if it's if the second, if you get a number for the second column,
Yep.
would you solve, did you use E?
Yeah.
Solve for that number, or did
No.
you use 0 to solve?
I never solve remember to solve this number here, it's -1/10 time determinant of always the first row and then 1 to the right. I never use the same row it's in to solve for those coefficients, right? So E doesn't enter into the picture until I move to the S1 row. Anything in the S2 doesn't even care that E is there. I leave 0. Yeah, once I do the next, once I verify that the second coefficient in row S2 is it's not a 0, then I substitute E. So it's like a multi-step process, right? Here's step 1, I got a 0. Then I got to go over here for step 2. I verified it's not a 0, and then step 3 is here. So you can't make it an E until you verify that you do not have a row of zeros. Got it?
Yeah.
Plug in what? I don't understand.
If you do have a row of all zeros.
Into the characteristic equation?
What do you use if you have a row of all zeros?
Auxiliary equation? You go, so this is the row of zeros here, right? If K is equal to 10, this is a row of zeros. So I go up to the S squared row, and then I use this coefficient and this coefficient, and I just plug it into there. This S squared term is from the fact that I'm grabbing it from my row S2. And just like when we do the Ruth Hurwitz approach, we have to skip a term. You notice it's S squared and not S. It's S to the 0, right? So I'm skipping the S1 term. That's what we do in the Ruth Hurwitz. Okay. Any other questions?
What's that? Where do you put it?
You take the derivative of it. So you take the derivative of the auxiliary equation with respect to S, and then that goes in the S1 row. If you have a row of zeros, you can't use the E term and you're stuck, right? Because you'd be divided by 0. So you get your coefficients for your next row by taking the derivative.
Squared, but 20 will S 20.
Yeah, I would put 20. If I knew what K was equal to, that would be 20. But over here, right, I just did it generically. I did it with leaving the value of K. But if K is equal to 10, I can make it a lot easier, right? I can just have numbers. So if you put in 10 over here, and you put in a 10 over here, if you put a 10 over here, then I would have to do that a different approach. This is just showing you by leaving it as a variable. Make sense? Any other questions? All right. Let's get back to steady state errors. Oops, I'm going to clear this. All right, so this is what we finished up with last class with steady state errors, right? We have a system type, and we have the 3 different inputs. And what we did, or what we solved for, was we had a position constant, a velocity constant, and an acceleration constant. And depending on what you're trying to achieve, right? We might be okay with a certain amount of error. All right. So we might not need to add much to our system to make it go away completely. Whereas if we have to have a system that has no error, we have to add more integrators into our system to balance out and make sure that we get rid of our error. So we can add we have a plant, which is our initial system, and then we can add a controller. A controller maybe is a PI controller, right? Proportional integral controller. There are things called lead lag controllers that sometimes you hear about. More in industry, you would see proportional and integral controllers. Lead lag has more to do with phase shifts and stuff like that, which you would need Bode plots. So you probably won't encounter them all that much in industry. But adding a controller can make things really useful. So let's take a look at an example. We have a plant, and we really didn't add a controller into it, right? I mean, we did, but we really didn't because it just multiplies by 1, so it's not really doing anything. So we added a controller in here to see if we can take our error away. Now, with this type of system, what type of system is this? There are 3 types that we've studied. I know it's been a week, so type 0 system, because the system type tells us the number of integrators or the number of S's in the denominator here. There's no S terms up front, right? Or if there is, it's 0. So this would be a type 0 system, correct? So we go back to our handy dandy table and we look and we see for the system type. So for this particular problem, we're just going to look at the criteria here. For a step input, we see that our error is going to be 1 over 1 plus k sub p. You can call that 1 or a, right? It just depends on the magnitude of the unit step. And we see for a ramp and a parabolic, it's going to be infinity. So the only system, whoops, that we need to calculate anything on is a type 0 system with a step input. Now we have to solve for k sub p, which is a limit as s approaches 0, g sub c times g sub p. So it's a type 0. What's the open loop transfer function? 1 times s plus 2 all over s plus 1 plus s plus 5. What's the steady state error? Step input. You do the limit as gc gp s approaches 0, and you get 2 over 5. And we'll just say that this has a magnitude of 1. Plug that in, and we end up with 5 over 7. That's our steady state error. Okay? For parabolic and ramp, I don't need to do any work because I already know that those are going to be both infinity, right? So there is no work that needs to be done. Okay, there's KB, and then there's KA. Now, let's actually make this system a little bit fancier, and let's actually add a proportional controller. A proportional controller means we have a variable value of gain that the controller is going to just have its error. It's going to multiply by a value or be proportional to whatever the error is. What changes here? If I put a value of K, what changes? It's not a tough question. Isn't this K? This is GC, right? This is GP. Isn't that K? So doesn't this become K over here? Which means that this, the limit as s approaches 0, this becomes essentially K multiplying out front is 2 times K, correct? So when I do my steady state error, I have 1 over 1 plus 2K over 5, which is equal to 1 over 1, or 5, I should say, plus 2K over 5, which is equal to 5 over 5 plus 2K, correct? That's what our steady state error is going to be. So what does that tell me? Increase the value of K, right? If K goes up, ESS goes down. So by adding a proportional controller, you can reduce the amount of error, steady state error that your system is going to have, but you can't make it go to 0. So the addition of a proportional controller is fine as long as you can tolerate some, maybe small, but some amount of error. And obviously, if you wanted to make the error go to 0, right, what would you do? You'd make K infinity. But last time I checked, you can't buy a proportional controller that has an infinite value or infant gain, doesn't exist. So you can get it smaller, but you can't get it to zero. So that's why when you add a controller that's proportional, you can reduce the amount of error. You can make it more tolerable. So here's a simulation. So you see, excuse me. You see, I'm bringing out my error signal. Terribly sorry. And comparing the input and the output. And what I see is when I hit the input with a unit step, that's what switch position shows. I go up to my normalized value of 1, and then my output ramps up a little bit, but then eventually dies out. And I've got some error between the two. Okay. And that's 5/7 or about 0.71, which is pretty high, right? When you're considering you're trying to get to 1 and you're up by 0.71, that's a pretty high value. Let's go to ramp input. What do you think the ramp input's going to be? Well, in the previous slides, we determined, right? It was going to go to infinity. So you see that the input is trying to keep up, right? It's ramping up, but it's ramping up slower than the input is. And so what happens is my steady state error gets bigger and bigger and bigger as my ramp continues to increase. So this would have a steady state error of infinity. What about here? What's the system type? It should be very easy to answer at this point. Type 1, right? Because you have one integrator, correct? And now the modification is we have a value of K, and we want to have a system that has no more than a 10% steady state error. So we want to pick the value of K for a proportional system. I mean, a proportional controller, I should say. So we get that value. Now, type 1 system, what type of input should you consider? Go back to our table. It's a type 1 system. So I'm moving down to here. So I know for a step input, you're always going to get 0. It doesn't matter what the value of gain for K is. It's never going to be greater than 0. Over here, with a ramp input, I see that I can get a steady state error there, and I want to limit it to 10%. Parabolic, I'm out of luck, because there's nothing I can do to my value of K that's going to make that disappear. So the only one I'm going to worry about is the ramp input, because for a step, I got it by default. In a parabolic, there's nothing I can do to make it work. So I'm going to go ahead and look at a ramp input, which means I have to use my expression here. Limit s approaches 0, s times GCGP. Sorry. So I can see I'm going to cancel out my S term, and I'm going to allow my limit. So I have 5K over 336, right? It's just 6 times 7 times 8. That has to be less than or equal to, well, the steady state error has to be less than or equal to 10%. So that 1 over K sub B has to be less than 10%. Or if I leave this generically as A, 336 times A, let me just go ahead and show you, right? Because this is A over K sub B, which is equal to A over 5K over 336, in case you're wondering how I ended up with that. So I want that to be 10%, and I'm going to just pick 10% of its final value. So that means I will go 0.1 times A, which means, whoops, I'm going to erase that. My value of K should be at least 672. You don't want it to be less than 672 because it'll give you more than a 10% error, right? Why can I tell? Because K is in the denominator here, right? So if it goes less than 672, you're dividing by a smaller number, which is going to give you a higher amount of error, right? But by increasing the number, we're going to get lower fraction, so we get the 672. Here's a simulation, and I'm not even looking at a step input because I know it's going to be 0. Here is my output, and it's really hard to see, but the blue line right here is R of T. And if you look kind of closely, you can see a red line sort of underneath it following along, but it eventually is able to track it. So maybe there's a little bit of error up front, but then it's not too bad. So this is a system that gets no steady state error, or a very small steady state error, I should say, less than 10%. And here is where you zoom in and look at the error in a little more detail. You can see it rings a little bit at first, and then eventually dampens out to 10% steady state error. Last error we'll look at is if you have a disturbance. So a disturbance is something in the process is changing for one reason or another. Maybe you've got a bad valve and it's not responding. And so instead of treating that as a completely new block diagram, you have a disturbance. So we add the disturbance in, which means we can use linear, the concept of superposition because it's a linear system. We add it in. And our total steady state error is steady state error due to the input plus steady state error due to the disturbance. So here is the first case. This is the superposition for the input only. Then we're going to add to it the disturbance input, right? Which means over here, that term goes to 0, right? So if I do plus minus, if this is no value, then I can just run that through. I don't have to worry about that. So I can just bring it around. So here's my ESS or E of S written in terms of the input and the disturbance. And this is, again, just using the block diagram approach. Now my limit using the final value theorem is going to be these two terms. And this is the only modification I need to add. I need to subtract from it that value. And I can't use the case of A and case of P and all that stuff. That doesn't necessarily apply. But if you do need to add a disturbance, you can add it in there. Now, the last one, remember we talked about you can calculate steady state errors for non-unity systems. The problem is that you're not getting really an error. You're getting sort of a different signal. So as we see over here, here's our input, right? That's our R. And here's our output. And then back over here, we're getting this EA. That's not the actual error between what we want and what we have, because we would be comparing R minus C to give us our actual error. That doesn't exist over here. So we got to tweak it a little bit, which means we need to convert to unity feedback. How do we do that? It's just block diagram math. Oh, and this is a typo. I apologize. That should be G1. What I need to do is I need to combine that half. I need to move that into the block diagram. So I need to move my summing junction to the other side. And if you look back at moving your summing junction to the other side, all I need to do is divide my feedback by whatever that feed forward gain is. And then I've got my value here. So this right here is a result of combining those two. I want unity feedback, okay? I want to be able to compare the input to the output. So what I want is this, right? But I can't get something for nothing. So I have to do some algebra. If I add 1 over here, don't I have to subtract 1 to get 0? I want to add 0. I don't want to add 1. I want to add 0. So the negative 1 that I have over here, this is positive C of S. This is negative C of S. I'm actually adding those two over here. So essentially, when those two get added together, I'm adding 0, right? The positive 1 and the minus 1 will cancel each other out. So I have to add this negative 1 block just to cancel out the fact that I want a positive 1 in there. And so I can move the -1. It's no big deal, right? Because I can move this to this summing junction. And I can combine that into here, H1, G1 minus 1. Now I can combine these two blocks into one using the G over 1 plus GH. And now I have a unity feedback system. Okay. I have, this is my plant, and this is H, which is equal to 1. So if you're really trying to calculate steady state error, you have to go through this process to be able to compare R to C. It's not hard. It really is just this step over here to make that work. All right. Okay, let's take a look at a simple example. We don't have a transducer on the input. We do have an H, a feedback loop, or a feedback gain that is not going to be equal to 1. So that's 1 over S plus 1. We need to add the -1, right? So what we see is there's no G1 term over here. This is what we did before. So this is equal to 1, and that is equal to 1. Now, this H1 is right here. This G1 is equal to 1. So all we need to do is substitute our values in, and we see G1 is equal to 1, G2 is equal to 100 over S plus 4, and H1 is equal to 1 over S plus 1. Now I go ahead and I combine that into one block diagram. So put all those numbers together. G1, G2 over 1 plus G1, G2, H1, G1 minus 1. Simplify the math a little bit. And I end up with 100S plus 100 over S squared minus 95 S plus 4. This is a little bit of algebra. I mean, if you need me to do that, I certainly can. Does anybody want to see the algebra associated with that to get that value? Yes? All right. Let's plug it in over here. So the first thing I'm going to do is I'm going to put this under a common denominator, right? So it makes it easier to multiply that out. So I have 100 over S plus 4 all over 1 plus 100 over S plus 4. Common denominator here is 1 minus S minus 1 all over S plus 1. Everybody see that? S plus 1, if I put this whole thing under S plus 1, then I have to multiply the numerator. Here, I might have done it too fast. Right? And then when I multiply that out, I have -1, not -1, +1. Minus, so this is 1 minus S minus 1 over S plus 1. If I write it out. So then I have this. These two terms will cancel. And all I'm left with is -S over S plus 1. So let me write that over here. S plus 4. And I have a -100S up there, right? Because when I multiply those terms, I get that. Now I'm going to go ahead and do another common denominator. 100 over S plus 4 all over S squared plus 5S plus 4 minus 100S all over S plus 1 times S plus 4. Everybody see that? All I did was multiply. I did I foiled these two, multiplied it by a +1, and then I subtracted the -1. So if you foil S plus 1 times S plus 4, you get that value. Now I invert and multiply. I have 100 times S plus 1, because the S plus 4s will cancel, right? And that's all over S squared minus 95 S plus 4. Everybody see that? Anybody not see that? I mean, I need some feedback to know if I Got it? So a lot of it is just common denominator and invert and multiply, right? It's the same process over and over and over again. It just becomes a lot of math. So 100 times s plus 1 over s squared minus 95s. Looks like we got the same thing, right? 100s plus 100 in the numerator. We have 100 times s plus 1. In the denominator, s squared minus 95s plus 4. S squared minus 95s plus 4. So that's our G sub P. We don't, I mean, G sub P. We don't show a G sub C. So now we can start to look at this and look at, for steady state error, what type of steady state error? Well, it's a type 0 system because there's no S multiplying it, right? There's no integrator in there. So we would go back over here. And for type 0 system, we see for a step input, we get 1 over 1 plus Kp, and then ramp and parabolic or infinity. And here's our unit step. Our unit step is just going to give us the limit as G approaches 0, or S approaches 0, G. We can see that that's just going to be 100 over 4, which is 25. And then our steady state error is 1 over 26. If it's a ramp, no work to do. Here's our simulation. We have a step and a ramp. And this is the original system, right? This is not the system that we converted to unity feedback. So here is our C of T. Here's our output. Here's our input. And this is for the unit step. How can you tell? Because look at R, right? It's step input. And it's hard to see, but red is not directly on top of blue. You can see the two. So there's a small amount of error. If I compare it for my E of T over here, I get, it's hard to see, but it's 1 over 26. So it's not exactly at 0. It's 1 over 26. It's a pretty small number. All right, here is what it is zoomed in quite a bit. So you can see the C of T. Now you can clearly see it's not 1, it's 0.96. And my steady state error is right around 0.04, right? Which is almost 1 over 26. So that's way, way, way zoomed in. Okay. Questions on steady state errors? Because that finishes that topic. And what I'll do is I'll assign a homework, but I won't assign it. I mean, I can put it available now if you want, but I was thinking of doing it on Thursday. So you can just focus on the test. If you want, I can make it available now, but usually it's less stressful if you see it. Well, that's typically the case, but we'll see. That's you got a good attitude about it. But for me, I type A, I like to get things done. And so I would see it and then I would think about, okay, how am I going to get this done? And I try to formulate all these, like, well, if I do it here and I get time here, and then it starts adding an extra stressor to me. So now I'm not as focused on the test as I should be. I'm stressed. So that's why I try not to do the homeworks, but you all are a lot different than me. So I can put the homework up if you want to know. And I won't make it due until next Thursday. So who wants to see the homework today? One person? Who wants to wait till next Thursday? Anybody in TV land have an opinion? Because it was almost unanimous in class, and I'm happy if you want me to just email me and I'll send it to you if you'd like it. I'm not doing that to single you out, but if you want to see it, I'm happy to. That's a good solution, right? So I'll make it available on Thursday. Sorry. I wish I wasn't baking. This is really obnoxious. Been a lot of rough nights sleep. Last night I had pretty bad chills too, so it might be the flu or I don't know. Yeah, it was pretty rough. Yesterday was a rough day. For those of you who were in lab with me, thankfully we had a bunch of motors running. It was so loud that you probably couldn't hear me cough and hack the whole time. But the solution is, this is like come up with a master solution. I'll make it available on Thursday. If anybody wants it earlier, just email me and let me know. I will be happy to send it to you. How's that for a perfect solution? That way everybody gets what they want. Okay. All right, any other questions, comments, concerns?
Are these slides posted yet?
I thought so, but if they're not, I will make them available. I'll double check that. Anything else? I could start our new material, or we can get to starting the study early. What do you think? Some people are closing their notebooks, so is that any indication? All right. Well, have a great day. I will be at the test tomorrow. Last time I had to go to Portland for my dad's eye appointment. But I've made different arrangements, so he's actually going again tomorrow, but I don't have to actually be there. So I will be at the test. All right. And don't forget, if you want to take the test remotely, some people have already emailed me, but just make sure if you want to take the test remotely, then let me know in advance. Okay. Have a great day, everyone, and I will see you folks tomorrow. Take care, everyone.